Welcome to the Explainer. I am absolutely thrilled to have you here today, mostly because we're going to look at something you've probably held in your hands hundreds of times, but never truly seen. Today, we're exploring the fascinating, entirely invisible microscopic engineering behind everyday optical discs. I'm talking about the hidden architecture that defined a whole generation of media.
So, I want to start by shattering a major preconception right out of the gate. When you hold a CD or a DVD, you just see a flat, shiny piece of plastic, right? Well, did you realize that your favorite movie, or that classic album you love, is actually carved into literal, microscopic mountains and valleys? It's not just a smooth mirror at all. It is a rugged, physical terrain of data.
Okay, let's dive right into this. To a computer, all information is simply binary data, a long sequence of zeros and ones. But on an optical disc, that binary code is mapped out into a physical, microscopic landscape. This terrain is made up of flat, elevated areas called lands and carved out indentations or holes called pits. The physical geometry of the disc is the data.
Section 1. Hidden topography of data.
To really grasp how this data is accessed, we have to look at the two halves of a single system. On one side, we have the optical media itself. This is your passive physical hardware like your CD or Blu-ray. And the crucial thing to understand here is that unlike an old-school magnetic hard drive that uses concentric circles, an optical disc stores all of those pits and lands on one single continuous spiral track that runs all the way from the center out to the edge. Now on the other side, we have the optical storage device. This is the active mechanical hardware, like your disk drive, which comes equipped with incredibly precise lasers designed to trace that massive continuous spiral track.
Section 2. Reading data with light.
The physics of this reading process are just remarkably elegant. Let's slowly step through exactly how a drive actually extracts information from this tiny mountain range. Step 1. The device shines a highly focused laser beam directly onto that spiral track. Step 2. When that beam of light hits one of those flat, elevated lands, it reflects straight back up to a sensor. But then, Step 3, when that exact same light hits an indented pit, the sudden change in depth causes the light beam to scatter.
And this brilliantly illustrates the exact moment of data translation. See, when the light hits that pit and scatters, it creates what physicists call destructive interference. The sensor inside the drive doesn't actually feel the physical bump. Instead, it reads the precise changes in light intensity caused by that scattering. The reflection off a land gives a high-intensity signal, and the scatter inside a pit gives a low-intensity signal. Just by measuring those incredibly fast fluctuations in light, the drive perfectly reconstructs your binary zeros and ones.
But you might be wondering, how does that terrain even get there in the first place? Well, it all depends on the formatting state of the media, and we basically have three main levels of permanence. You've got ROM, which stands for read-only memory. You have -R, which means write once. And finally, you have -RW, which stands for rewritable. The CD-ROM discs, like those movies you buy at the store, are permanently pressed at a factory. They're completely locked down. You can't overwrite them. But consider the middle state, the R or write once disc. When you buy a pack of these, they are completely blank. Your device's laser literally etches the pits into the surface in a single write cycle. And the really cool part? Once that laser etching process is done, that R disk behaves identically to a permanent ROM. And finally, the RW relies on this dynamic phase change material that allows the laser to erase and rewrite the terrain repeatedly, which is obviously perfect for continuous data backups. Section 3. The evolution of capacity.
As computers grew more advanced, we naturally needed to store vastly more data, but, the physical disk couldn't get any wider. So to engineer the DVD and get exponentially more storage, they used a secondary trick of optical physics, variable focal depth. A DVD utilizes a dual-layer system. A specifically tuned red laser can actually focus through a semi-transparent top layer of data to read an entirely separate solid bottom layer. It's literally like reading two distinct landscapes stacked right on top of each other.
And dual layering was really only part of the solution. To seriously boost capacity, you have to follow the absolute core rule of optical physics. Data capacity is dictated by the color of light. If you want to cram more data onto the exact same size disk, you have to make the pits and lands smaller. And to read smaller pits, you essentially have to sharpen the pencil. A standard CD used an infrared laser at a 780 nanometer wavelength. By shifting down to a shorter, 650 nanometer red laser for the DVD, the beam became much finer, allowing it to accurately read a vastly tighter, smaller data topography.
So the absolutely crucial point here is what happens when you push that physics rule even further. Engineers eventually made a massive technological leap all the way down to a 405 nanometer wavelength. At 405 nanometers, the laser is no longer red. It sits right in the blue spectrum of light. And this tiny, incredibly sharp blue laser gave birth to the Blu-ray disc.
Because that blue laser was so incredibly fine, it allowed the microscopic pits and lands to be carved smaller than ever before. This skyrocketed the storage capacity of a single-layer disc from a standard DVD's 4.7 gigabytes all the way up to a massive 27 gigabytes. And this tremendous leap in space didn't just mean better-looking movies for us. It allowed for complex interactivity directly on the disc itself, like space searching and creating dynamic playlists.
Take a second to digest these specs, but notice the track pitch specifically. That's the distance between the spirals of data. On a CD, the track pitch was 1.60 micrometers. By the time we get to the blue laser of the Blu-ray, that track pitch has shrunk all the way down to an incredibly dense 0.30 micrometers. That right there is how you get 27 gigabytes of data onto a piece of plastic the exact same size as a 700 megabyte CD. Moving on to Section 4, evaluating the diagnostic balance.
Now, while this whole system was a brilliant feat of engineering, every technology eventually hits its limits. On the positive side of the balance sheet, optical media offered incredible portability. They were thin, light, and dirt cheap to produce. Furthermore, ROM data offered a durability that magnetic hard drives just didn't have. It was permanent, immune to accidental deletion. But those pros were ultimately weighed down by some severe physical limitations. Their physical fragility was a major problem. A simple surface scratch could literally destroy the data path. Additionally, mechanically rotating a disk just to find information is vastly slower than modern solid-state access. And finally, even a 27 gigabyte capacity ceiling is easily dwarfed by the multi-terabyte hard drives we use today.
Section 5. The Architecture of Obsolescence.
Those physical limitations inevitably shifted the entire macroeconomic landscape. As modern computing evolved, consumer demands for instant speed and immense capacity just skyrocketed. Because a physical laser takes actual time to move across a spinning disk, optical media simply couldn't keep up. This drove the market to adopt three major replacements. First, flash memory, like your USBs and SD cards, providing instant, smaller, faster access. Second, the cloud, offering a secure, locationless storage. And third, streaming platforms, which completely eliminate the need to physically own a copy of the media at all.
Let's see how this builds our modern digital era. Look at how directly these physical limitations map to the solutions we use today. Slow access speeds, solved by the microchips of flash memory. Physical fragility, solved by the off-site redundancy of the cloud. And the limitations of physical capacity and ownership were entirely bypassed by the infinite library of streaming. We eagerly traded our physical hard copies for modern digital convenience.
But as we wrap up this explainer, I want to leave you with one final thought. The engineering of the optical disc gave us something incredibly unique. Hard, permanent data carved into a physical landscape that you could literally hold in your hand. So I ask you, what do we lose when we trade the permanent, physical topography of a CD-ROM for the invisible, rented convenience of the cloud? It's definitely something to think about the next time you happen to hold a scratched, but deeply permanent CD. Thank you so much for joining me to uncover this hidden world. Keep questioning, keep learning, and I'll catch you next time.